Hello. In this video, we're going to take a look at covalent bonding. Now, covalent bonding is something you've probably learned in younger grades, and it is essentially the sharing of electrons. So we have like covalent bonding is sharing of electrons. But it's actually more than that. It's actually sharing of electron pair. Usually one electron from each atom in the kind of sharing. And since it's covalent, it means like covalent electrons, like they're sharing them. And what it usually involves is we have a positive nucleus, and then around that we have our orbit or orbital. Then we have another kind of positive nucleus, and the orbitals overlap. And in between we have one electron and two electrons. Now, with the two electrons in the middle, the nuclei have this kind of electrostatic attraction between the positive nucleus and the negative electrons on either side. So this is another kind of electrostatic attraction. Very similar to our ionic bonding. So our ionic bonding was between a positive and negative ion. Now this one is between the positive nuclei and the negative electrons between the two nuclei. So they kind of like pull on each other, like kind of a tug of war. And that's essentially what the covalent bond is. It's all this kind of like pulling between them. And this actually makes it very strong and very tight. Also because with the overlapping of the electrons, these electrons are relatively close to the nucleus. And actually, the more overlap we get with the orbitals, and the closer they are to the nucleus, the greater the attraction, and therefore the stronger the bond. So we tend to get this between all sorts of different atoms. So if we want to move this over here, this electrostatic attraction, we tend to get it between atoms of the same kind, so like N2, O2. We can see it in like different elements, like our favorite water here, or carbon dioxide. We even see it with kind of elements more towards the middle, so we get carbon tetrachloride, CCl4, methane, silane. So all these kind of different things, they bond together covalently. And when they bond together covalently, we get all this kind of overlap and like get the sharing of these electron pairs. And it's not only just the sharing of the electron pairs, but it's also because of the nuclei and its attraction. So generally, nonmetals, here these are nonmetals only, let's not forget that. They are going to want to have a noble gas electron configuration, and when they bond together with other nonmetals, the only way they can do it is share. But there are actually exceptions to this kind of octet rule or noble gas configuration rule. We have something like boron. Now boron has, if I do my Lewis structure, only 3 electrons. And because it only has 3 like kind of unpaired electrons, it can only make 3 bonds, say with hydrogen, like so. So I draw that. And because it can only make 3 bonds with hydrogen, it can only really have access to 6 electrons. So this is a very stable compound, but it doesn't quite have the 8 electrons. It doesn't really, it's not really isoelectronic with a noble gas. We also have others that will exceed their octet if they share too much. So if you take a look at my water, so H2O, we have oxygen, and it has 1, 2, 3, 4, 5, 6 electrons. So it's not going to share with all 6. it's only going to share with 2. It only needs 2 more electrons. So the hydrogens, they're going to share just with these 2. So that hydrogens, they get the 2 that they need, because they only need 2 to fill up theirs. And the oxygen gets its full 8. But if I get a little bigger, and I extend beyond the 3rd period, or go into the 3rd period, I should say, I can have elements that will go beyond their octet. And these are very, very much like sulfur. Sulfur can actually have 6, so we can have SF6. Or we can have like phosphorus. Phosphorus can be like PCl5. So they're actually, in this case, sulfur will have access to 12 electrons, and phosphorus will have access to 10, as opposed to here with my oxygen, it only has 8, as kind of per usual, or the norm. Not quite the rule, but more the suggestion. So because we have these sharing of electrons, it's okay. It's just like it has energy within its orbitals to kind of expand beyond. These are just kind of the exceptions. But with covalent bonding, it's always important to remember that it's just between the nucleus, here I'm going to draw it, and this outer shell. That's all it really is. It's just this electrostatic attraction. And it can happen in a bunch of different ways, but it's just basically this electrostatic attraction. And this electrostatic attraction, as a reminder, will also give it unique properties. The nonmetals and the covalent bonds, they tend to be molecules, so they tend to be like self-contained units. So H2O, or my SF6, or CO2, N2, or any of the Hofbränkels, they're self-contained, unlike the ionic compounds, which are big compounds, and they go on forever, and you can't really have an individual molecule. So this gives them unique properties. They don't conduct electricity, so don't conduct for the most part, because they have no free electrons. So, because no electrons are free to move, either like for the ionic bonds, they can break apart and they can have electrons on the ion to move from one side to the other. No free electrons. In metals, like they have this whole sea of electrons, they can move from either side of the sample to the other. They also are not soluble in water, so they don't dissolve. And they tend to have low melting points and low boiling points, which is why they are liquid or gas at room temperature. So, and it's because they're liquid or gas or room temperature, that's the ones we kind of see a little bit more, like they're the ones in the air and the ones we explore a little more and more familiar with. And in a future video, we'll kind of get into the intermolecular forces, which kind of deal more with both their bonding types and how these intermolecular forces play a role in either their melting point or boiling point, and really what does this interaction at a macro scale really mean.